All right. Yeah. Hi, everyone. My name is Chris, and today I have Johnny with me joining in remotely, and we will talk about the OCP DeltaLake OSF how-tos and features. And Johnny will take it from here in the first place.
All right, everyone. My name is Johnny Lin. In this talk, I will present OCP Server DeltaLake OSF how-tos and OSF checklist. Christian from Element, he will present their works on security features. In this talk, I still refer Meta as Facebook. So next slide. Here's WeWin's OSF journey. It's a joint collaboration with Facebook, Intel, and Element. Starting from 2019, we work on Model Lake and develop features for IPMI, SMBIOS, ACPI, and board configurations. In 2020, we continue our works to Tiago Pass and Delta Lake. Facebook and Elements develop ROS and security features, and we also did some performance optimization. In 2021, we submitted OSF checklist for Delta Lake, and it just got OCP accepted. The overall features have reached pre-production readiness. In 2022, we have been working on Intel Sapphire Rapids. CXL memory device support will be added, and we target for production readiness. Next slide. Here's the link to OCP OSF checklist and a link to Delta Lake OSF checklist for your reference. Section 1.2 of the checklist lists the required artifacts that we need to submit. A firmware image, description of the firmware ownership model, top-level build script, documentation, test results, tool for user modification. I will introduce most of the items here. Next page. Thanks. Section 3 of the checklist is ownership and reusability. For Delta Lake, the OEM key and Intel CBNT security profile can be fused onto the PC edge. So there are 3 options for customer to choose from. A, customer could choose whether to fuse or not and how to fuse depending on the customer's threat model. Or B, customer could choose to use different profiles of Intel CBNT or to use core boot's verified boot. Or C, if Delta Lake was fused with other owner's OEM key, transfer of ownership is not possible. The next owner can use it without Intel CBNT. Section 6, test regimes. The firmware must be able to do code and won't reboot to an OSI-approved OS over 100 times. Next page. How to download and build. So here's the link to Delta Lake on OSF GitHub. You can find all the information and details there. After git clone the repo, you simply run download and build shell script, and it will download the Intel public blobs, including FSP, PCH ignition firmware, microcode, and it will download the toolchain, core boot, and Linux boot source code by Osf Builder, and finally, it will run make to build the image. Next page. This is the Osf architecture at Facebook. It's called core boot Linux boot. The box on the left represents the firmware image. Core boot and FSP do the core chipset's initialization and jumps to a Linux payload, which is called Linux boot. It provides rich Linux utilities written in Go. And finally, it can boot target OS through KZAC. The target OS can be booted either over network or from local storage. Next. Osf Builder. It was developed by Facebook, but now it's also forked under Linux boot GitHub. The core of Osf Builder is getapps, a tool written in Go that can fetch OSF components described by JSON file. The supported components are core boot, kernel, and initRANFS. Here's the link to an example of a QAMU JSON file. You can see the URLs for core boot and the toolchain that will be downloaded by the tool. It provides an example for QAMU, and we encourage you to try out and play with it. Next. Firmware configurations. Our firmware configuration is using command line interface and uroot shell. The configurations are stored in BPD region. It's a flash region for storing key value pairs. There's an open source Linux utility called VPD that can decode the key value pair. Read-only VPD is the flash region hosts the default value. Read-write VPD is the flash region hosts the customized values. The firmware would use the values in read-write VPD first, and then read-only VPD. FlashRun is an open source Linux utility for BIOS flash read-write. From the picture, the VPD utility would call FlashRun to do flash region read-write. Currently, we execute the two binaries for these operations, but they might be implemented as UROOT packages in the future. So the CMOS clear that should restore configurations back to default can be done by reformatting read-write VPD region. So the VPD values will fall back to read-only VPD region. Here's the link to the UROOT commit for your reference. Next. Here are some examples. This is the link to all the firmware configurations used by DeltaLake. For boot order, we use system booter UROOT packages for describing boot interface. In this example, the first boot order VPD variable, boot 0000, is set to netboot DHCP IPv6. The second boot order is set to local boot using grub. Another example is FSP log, disable or enable that can be controlled by VPD variable FSP log enable being set to 0 or 1. We use VPD boot manager and UROOT command line utility for managing boot VPD variable. For example, get will print a variable value, set will set a variable value, and delete will delete the variable. Next. Here are the executions screenshots of VPD boot manager. Read is done through VPD CCFS kernel interface. Write is done by executing VPD and FlashRun binaries. The first example, we get a value of FSP log enable, and it shows 0. In the second example, we set it to 1. Next. Here's the link that documents DeltaLake OSF features, including system tables, BMC integration, support devices, OS booting methods, security features, Rust features, performance test rerun. You can find more information from the link. So this is my presentation. Thank you. Back to you, Chris.
All right. Yeah, thanks, Johnny. So yeah, I'd like to talk about Intel CBNT right now. So actually, that's the TLDR of my presentation, right? So if you only want to watch that one slide, it's basically enough. So we got an open source implementation of Intel CBNT in coreboot. We got open source tooling, so full open source tooling to provision and actually validate Intel CBNT. We got, of course, you have to pull in some closed source binaries, the ACMs from Intel to make it running, and Profile 0T is basically production tested. But yeah, let's step back a bit. Like, what is CBNT actually, and why would you need it? CBNT means Intel Converged Bootguard and Trusted Execution Technology, which is basically before CBNT there exists Bootguard and TXT as like standalone products. Nowadays, Intel merged that together into one technology. It provides static and dynamic root of trust for measurements. The purpose actually of Bootguard is to verify that the initial firmware, like the first code that actually runs from the firmware part, is supposed to be good, right? So it should have the same hash values. And TXT, and I actually took that from the spec, I guess. The primary objective of TXT is enabling platform boot into a secure measurement launch environment. So that's the dynamic part here. Okay, what happens in CBNT? So basically, Intel removed the trust anchor that in TXT was in the TPM. They basically moved that into the ME. So you got fuses in the ME, where all the firmware security is actually rooted in. You got one set of ACMs for TXT and Bootguard. Before that was actually not the case. And the most configuration of the firmware and how the security is set up and laid out is basically in the binary structures now, which is namely like the key manifest, the boot policy manifest, fit tables or the fit table, and of course you need a little bit of ME SPS configuration there. I got a small overview on how CBNT works. So basically you got the Intel ME or SPS in the server space. You got a hash of the signing key of the key manifest fused into the SPS fuses. So that is like a one-time fuse and off you go. The key manifest basically gets checked by the ACM in the first place. Then you extend that root, right? So the left part basically is your root of trust that gets checked through the ACM, and once you're at the KM, you start your chain of trust lying out so that you check the key manifest actually has the hash values of the BPM signing key in there, and also the ACM checks that signature there, and within the BPM then there are IBBs defined with corresponding hash values. Where your IBB gets checked, right? So that is basically like the left three pictures are basically like the root of trust, and from the IBB basically you start off building the chain of trust. How do we do it in coreboot? Coreboot, so all the code you can actually find online upstream. Everything is in source security Intel, and then you get like TXT and CBNT directories. We leverage most of the TXT code that was already there from a former implementation of TXT. However, we added like CBNT logging for mostly for debugging purposes. We integrated everything and have it configurable via the coreboot build system, and that includes the Converged Security Suite as a dependency, which is actually there to generate and signs all the binary structures. And we have the build system that includes like generating that KM, signing everything, like all the structures that are there. You can define options which we can write into KM and BPM. We inject the fit entries and also the ACMs. Timeline-wise, when we started in September 2020, basically we wanted to implement CBNT. However, or let's say like we got the first POC booting, like the proof of concept that it actually works, and the code was not so nice by the time, in November 2020, right? So booting into T-boot and having everything verified. So that means from zero actually to getting the POC up and ready, it took us 2 months, which included writing all the open source tooling to generate KM and BPM. Another 4 months, so 6 months in total, it took us to have everything integrated in coreboot, like in the build system, that everything gets generated and signed automatically, that you can put in all the artifacts, and everything gets included automatically into the binary, final binary. Also, coreboot is able to automatically detect all the IBBs that are there and add those to the BPM. I gotta speed up a bit. You can find a demo, probably we can set up a demo at the Experience Center here at the OCP, so please just come by and check that out. We got a DeltaLake at least there, so we can do something. Otherwise, we're hanging around there and you can talk to us if you want to know more about it. Also, there's like a nice Eagle Stream demo coming up, which you can actually check out. Yeah, call to action, contribute to coreboot and Linux boot open source projects. Contact WeWin if you want to buy one of these wonderful DeltaLakes. You can contact us, 9Elements, if you need like professional support or feature development for the DeltaLakes or for coreboot in general. Here I listed basically all the links that you can check out to get more information, like coreboot, Linux boot, the Converged Security Suite, the Open System Firmware project on GitHub, and everything else. And I got 20 seconds left, so I don't know if I can take a question or not. That's it. Thanks.